Hello everyone, my name is Ona Givert and today I will present our submission to the shared task on translation into low-resource languages of Spain. This shared task has been held at WMT, hosted within NMT 2024. The title of our work is Hybrid Distillation from Rule-Based MT and Neural MT. This is the result of a collaborative effort with the colleagues at Helsinki-NLP lab. Now, let's get started. What is the task about? The task consists in a translation task to translate from Spanish, a high-resource language, into Aranese, Aragonese and Asturian, three low-resource languages of Spain. Asturian is spoken on the northeast region of Spain, while Aranese and Aragonese are spoken on the northwest. Aranese is a variant of Occitan that you can see down there in the legend in the map. Let's move on to our submission. The first step that we took was to assess the current landscape of available models. Basically, we were trying to answer the question, what is out there already? So we benchmarked different types of models. First, Apertium, which is a family of rule-based MT models for related languages. Then Opus MT models, which is also another family of openly available neural models. And finally, the no language left behind variants. We can see how Apertium models are actually quite good, and then if we compare them with Opus MT models, they perform really well, even better than the no language left behind variants on average. Furthermore, they are faster as they are much smaller in size. Based on this, we chose two Opus MT models for fine-tuning, the one shown in red, and in purple for back translations to produce synthetic data. And talking about data, which data did we use? We focus our efforts on data collection. We scrape data from dictionaries, we download new Wikipedia dumps, and we also collect Tatueva challenge data, which is the collection of the duplicated and shuffled data coming from Opus, one of the biggest public repositories of data. We also produce back translations of monolingual data into Spanish, and we apply thorough data cleaning. We use the language identifier given by the organizers to separate our data, and then we also use Opus Cleaner and Opus Filter tools, which are specifically aimed at data cleaning. With Opus Cleaner, we can visualize which filters of Opus Filter clean our data the most, and we choose specific filters for each corpus separately. Now, if we focus on the table, we can see the amount of monolingual and parallel sentences that we have for each language. As mentioned before, Aranese is a variant of Occitan, so after applying the language identifier, we split these two languages into Aranese and Occitan separately. In the final column, we can see the total amount of sentences available per language, and we can see that for Aragonese and Aranese we have much less data than Occitan, and then the most amount of data we have is for Asturian. The final size of the corpus that we use for our models is 4.3 million sentences. Now let's talk about our models. All our models are transformer-based. They use the Opus MT model in some way and have a separate source and target sentence piece vocabulary. The vocabularies, we take them from the Opus MT model. We don't train. We employ sequence-level distillation proposed by Kim and Rush. In sequence-level distillation, a powerful teacher teaches a smaller student how to translate, and that is done by simply forward translating all the source data to create a distilled dataset. In sequence-level distillation, we need a teacher and a student, and that is what it is illustrated here with the emojis. For our teachers, we take two strategies, although very related. First, we simply fine-tune the Opus MT model with our newly training data that we just described. However, since Occitan and Aranese are of the same family and very closely related, we also experiment with data tagging. Having multiple tags for a single source sentence improves the fine-tuning that we have in A. For our students, we take two approaches. First, we distill models from our best neural system, and then we take a hybrid distillation approach, which makes the most out of the neural and the rule-based MT systems. Let's start with C. We take each source sentence and we forward translate with our best neural system and we propose 8 candidate translations. Then we keep the candidate translation that has the highest HRF score with the target sentence. Then we create a distilled dataset and we trained our model on that distilled dataset. Similarly, for our hybrid distilled approach, we forward translate with our neural system and we produce 8 candidate translations, and then we also forward translate with the rule-based MT system, Apertium. Then we keep again the one hypothesis that has the highest HRF with the target sentence to create our distilled dataset. Let's look at the table of our development scores to get a better idea of how these systems perform. On column model, we see either if it was NMT distilled or a combination of NMT and rule-based MT distilled, then which teacher we use. You can find more details about them in the paper. Also, which size. We use transformer base, which is around 65 million parameters, and then transformer tiny. You can also find the details in the paper, which is a very fast transformer architecture that has 17 million parameters. Then the submissions that we have, and finally the scores for the different language pairs. At the time of submission, we didn't realize that for our model D3, the forward translation was done with the wrong tags. Therefore, a higher percentage of rule-based MT data was selected. After the submission deadline, we did 2 extra models. A fixed model with the current language tags, and also a model distilled only from rule-based MT data. And we can see that that's actually our best model. However, we didn't have time to submit. This definitely opens research into distilling from rule-based MT systems. And now we're already getting to the end, so let's see the results of the final submissions. We produce 4 submissions in different sizes and different methods. Our best models rank 4th, 5th, and 2nd in the open track, so we don't use any closed source data or models. And our best model is an accident, because our best model is actually the one produced with the wrong data tags. Our smallest model is 210 times faster than its teacher. You can see it in column 3. Let's look at the table for a second. On average, our models are 4 bullet points below the best competitor. And we can see that we employ different techniques such as fine-tuning, data sampling, distillation, data tagging, and also ensembling of the best checkpoints for submission. We also provide the parameters of our models and the speed. And as I have mentioned, our submission number 3, even though is a few bullet points below the baseline and the best competitor, is much faster. That is all from my side. I hope you have enjoyed this talk, and don't hesitate to read our paper or to contact me if you need any more details about anything. Thank you so much.